Hi folks, welcome to this lecture. In this lecture we are going to be looking at gases, and under gases we are going to look at the gas properties, we are going to look at gas laws, we are going to look at the partial pressures of gases, and we are going to look at gas stoichiometry. Now let's start by describing what gases are. So gas particles are spaced far apart, and there is very little interaction between the gas particles, as you see in the picture here. Now, if we look at the composition of air is made of about 78% nitrogen and 21% oxygen. So the rest of the 1% is made up of other smaller gases like methane and all the others. So we are going to look at what we call ideal gas, and there are two assumptions that we are going to make here. The very first one is that the volume of particles is much less than the container in which they find themselves, and the second is that the particles have no attraction for each other. Okay, now the properties of the gases that we are going to be looking at here are temperature, volume, and pressure. So we are going to be seeing how these properties vary. Now let's look at what pressure is all about. Pressure is the force that gases exert on their surroundings, and pressure is given by the formula force over area. Now, when you have gas particles in a container, the gas particles collide with the walls of the container, and as they do collide, the collisions leads to a force. They exert a force on the walls of the container, thereby generating a pressure. So the pressure of the gas is given by the force exerted by the gases on the walls over the area of the container. Now here you see this propane tank here that is it has propane inside the gas. So the gas inside this container, they exert a pressure as they hit the walls of the container. So they exert a pressure and they try to push the container out. And also the air particles, they also exert a pressure on this container by hitting the walls of this container. So all of that generate a pressure. Now, how can we measure pressure? So pressure is involved in everyday activity that we encounter. For example, the atmospheric pressure is involved with what is happening around us, and also that affects the weather conditions like wind. The change in atmospheric pressure will affect the wind speed and other properties. The basketball that you see here, there is air that is inflated inside this basketball, and it exerts a pressure. So the ball bounces because of the air that is inside the basketball. So the car tires are able to roll because there is air that has been inserted inside the tires and they exert a pressure. Okay, so these are all life situations where pressure is applicable in our everyday life. Now, pressure can be measured using what is called a barometer. So a barometer is a device that is used to measure atmospheric pressure. Now, how does the barometer work? Here is a tube, it's a long hollow tube. The tube is filled with mercury, and then the mercury is inverted over a container that contains mercury. Now, to be able to know the pressure, the gravity exerts a force here pushing down the volume, the mercury in this column. So the gravity pushes down the mercury in the column, and the air pressure pushes the mercury in the column, and there is that interaction. So what you see here, the height of the column is the pressure that is being exerted by the air, and that measures the air pressure. And the height of this mercury is in millimeters. So the pressure is measured in millimeters of mercury. Okay. Now, 1 millimeter of mercury is also equivalent to 1 torr. A torr is a unit of measuring pressure. Now, the average air pressure at sea level has been measured and found to be about 760 millimeters of mercury. Since 1 millimeter of mercury is equal to 1 torr, it means that is also equivalent to 760 torr, and that is called the standard pressure. So when you hear standard pressure, it means it is 760 millimeters of mercury or 760 torr. Now, let's see how the barometer works. We are going to take a very common example here that we carry out every day, and we will relate it to how the barometer works. Here you see this little beautiful girl using a straw to get a drink. Now what happens is that when the girl pulls up the air that is found in the straw, that reduces the air pressure inside the straw. Now the pressure outside the straw is greater than the pressure inside the straw, and then that forces the liquid to move up in the straw. So that is exactly the same way how the barometer works. So the air pressure here pushes the mercury inside the column, and it rises because the pressure outside here is greater than the pressure inside here in the vacuum. So when the pressure outside is greater than the pressure inside, it pushes the mercury now to rise in the same way as the little girl sucks up the liquid. The pressure outside is greater than the pressure inside. Now let's look at pressure gauges here. So what is a gauge pressure? What is gauge pressure? So there are so many gauges, and they have a particular way, so they are designed based on what they are used for. And what is gauge pressure? Gauge pressure is defined as the difference between the compressed gas pressure and the atmospheric pressure. So it is a difference between the compressed gas pressure and the atmospheric pressure. So if you measure a gauge pressure and you have a gauge pressure of 0, it doesn't mean that the pressure is 0. It only means that the pressure inside of the apparatus they are using is the same like the atmospheric pressure. So that difference will give you a pressure of 0. So if you have a gauge pressure of maybe 1, it means that the pressure inside the compressed apparatus and the gas and the atmospheric pressure, the difference is 1. Now let's look at conversion factors for pressure. We've already seen the millimeters of mercury. Now another unit of measuring pressure is called the atmosphere. You will see this most of the times, all of the times. And now you need to know the relationship between atmospheres and millimeters of mercury. So 1 atmosphere is equivalent to 760 millimeters of mercury, which is equal to 760 torr. Now in the United States, we measure pressure in units of pounds per square inch, and 1 atmosphere is equivalent to 14.70 pounds per square inch. 1 atmosphere is also equivalent to 101.3 kilopascals. So kilopascals is another unit of measuring pressure, and also 1 atmosphere is equivalent to 1.013 bar. So pressure could be measured in units of bar, atmosphere, kilopascal, pound per square inch, millimeters of mercury, or torr. So you need to know how to convert between any of these ones because you will be using them in calculations. Now let's look at the next part of this lecture where we are talking about the gas laws. And in the gas laws, we are going to be looking at the Boyle's law, we'll be looking at the Charles' law, and we'll also look at the combined gas laws. For the Boyle's law, what does Boyle's law say? Boyle's law states that the pressure and volume of a gas are inversely related at a constant temperature. So the factor here is that the temperature has to be constant. If the temperature is constant, Boyle's law states that the pressure is inversely proportional to the volume. So which means that as the pressure increases, the volume decreases. All right. Now, for example, that shows that the pressure times the volume will be a constant, because we've said pressure is inversely proportional to volume, which means that PV is a constant. Now, to demonstrate that as the pressure increases, the volume decreases. Here we have a gas, an oxygen tank that these firefighters are using. So the oxygen has been compressed, the gas has been compressed into this little tank, which means that the pressure inside the gas tank here is very high. Now, because PV is a constant, that means that P1 V1 will be equal to P2 V2. This formula will be used in calculations where we have P1 the initial pressure, V1 the initial volume, P2 the final pressure, and V2 the final volume. So you can be given three of any of these factors and you are asked to calculate one of them. So you have to master this formula. P1 V1 is equal to P2 V2. So this relates pressure and volume. Now let's look at this example here. A commercial compressor stores 2.8 liters of air at a pressure of 150 pounds per square inch. If this air is allowed to expand until the pressure is equal to 15 pounds per square inch, which is just over atmospheric pressure, what volume will the air occupy? Now, for us to be able to solve this problem, we have to collect the data that has been given to us. We already know that the formula that we are going to use here is P1 V1 is equal to P2 V2. And we are looking for the final volume, because the question is, what volume will the air occupy? So we are given the initial volume to be 2.8 liters, the initial pressure to be 150 pounds per square inch, the final pressure to be 150 pounds per square inch. Now we have to look for the V2. So let's collect our data. The P1 is 150 pounds per square inch. The P2 is 15 pounds per square inch. The V1 is 2.8 liters and the V2 is not known. So we are going to use this formula to make V2 the subject of the formula. So that is why the math review we did was very important. Now V2 will be equal to P1 V1 over P2. Okay, using that formula. Now we then go ahead and substitute in our values for P1, which is 150 pounds per square inch, V1, which is equal to 2.8 liters, and P2, which is 15 pounds per square inch. So after putting in the values, we now cancel out the units that appear both at the numerator and the denominator. So we have pound per square inch cancelling out, and our final units are liters. So if you do this calculation, you will see that the volume is 28 liters. Now, let me take you back to the formula. It says that the pressure and volume are inversely proportional. Let's look at P1 and P2 and see what happened. For P1, we had 150 pounds per square inch, and P2, we had 15 pounds per square inch. So what happened to the pressure? From 150 to 15, it means that the pressure reduced. And we know that Boyle's law states that pressure is inversely proportional to volume. Since the pressure reduced, it means that the volume is going to increase. So we see that our initial volume was 2.8 and the final volume is 28 liters. So that has been verified. Now let's look at the next law, Charles's law. Charles's law states that at constant pressure, the volume of a gas is directly proportional to its temperature. Here it means that as the temperature increases, the volume as well increases, which means that volume is directly proportional to temperature, and we are going to state mathematically that V over T is a constant. Alright, now let's see how we can use Charles's law to find absolute zero. Absolute zero is the temperature at which a substance has zero activity. Now, Charles used a graph here. He used different gases, and he discovered that as the pressure was reducing and reducing, all the gases had absolute zero at the same temperature. It doesn't matter which gas was used. As the temperature was decreasing, as the pressure was decreasing, there was a particular temperature where they both have zero, and that is called the absolute zero, which is minus 273 degrees Celsius, minus 273.15, sorry. So that is called the absolute zero. Now, let's look at the Kelvin scale. What I just showed you in that graph where you keep looking at the degree Celsius scale. On the Kelvin scale, the absolute zero will be equal to 0 Kelvin, because for the degree Celsius is negative 273.15. So for the Kelvin scale, it makes use of just 0. So it takes away the negative. Now, the Kelvin, how can you obtain the Kelvin from the degree Celsius? So if you are given temperatures in degrees Celsius, for you to convert them to Kelvin, you need to add 273.15. But what happens when we want to work to the nearest degree? If we are working with the nearest degree, we say that the temperature will be equal to the temperature in degrees Celsius plus 273. So that is how you convert temperatures from degrees Celsius to Kelvin. And likewise, if you have to convert from Kelvin to degrees Celsius, you are going to say that is Kelvin minus 273. So that is how you convert between degrees Celsius and Kelvin. Now, let's look at the situation where we can solve problems using Charles' law. We have stated that the volume is directly proportional to the temperature at constant pressure. So V over T is a constant. So mathematically, we are also going to state, as we stated for the Boyle's law, that P1 V1 is equal to P2 V2. We are going to state for Charles' law exactly the same, like V1 over T1 is equal to V2 over T2. So with these factors given to you, you can calculate either the temperature, either the final temperature or the final volume of a gas when you are given the initial, the final, the initial volume and temperature, and one of the finals. Now, let's look at this example. A balloon has a volume of 3.2 liters at room temperature, which is 25 degrees Celsius. The gas inside the balloon is then heated to 100 degrees Celsius. What is the new volume of the balloon? Now, let me state this categorically. Any question that you have to solve with gases that involve a temperature, the temperature must be converted to Kelvin. If you have the temperature in degrees Celsius, the first thing is that you must convert that temperature to Kelvin. If you work with the temperature in degrees Celsius, you will fail. Now, let's collect the data. The initial volume, which is V1, is 3.2 liters. The V2 is what we've been asked to calculate. What is the new volume? So that is what we are looking for. For the T1 is 25 degrees Celsius, but we must convert it to Kelvin. So that is going to be 25 degrees Celsius plus 273, and that gives us 298 Kelvin. For the T2 is 100 degrees Celsius, and we must convert it to Kelvin. So we add 273, that gives us 373 Kelvin. Now, we are going to state the formula that we use for Charles' law. So the formula that relates volume and temperature is the Charles' law, and we are going to see how we can find V2 from that formula. So let's state the formula. V1 over T1 is equal to V2 over T2. So in this case, we want to make V2 the subject of the formula. So if you want to make V2 the subject of the formula, that will give you V1 times T2 over T1. So we have all the information. We have V1, we have T2, and we have T1. So we substitute the values here and cancel out the units, and then we have the unit of temperature, the unit of volume, since we are looking for V2. So let's substitute. Our V1 is 3.2 liters, T1 is 373 Kelvin, and sorry, T2 is 373 Kelvin, and T1 is 298 Kelvin. So Kelvin at the numerator and at the denominator, we cancel it out, and we are left with our unit of volume. So we multiply 3.2 times 373, then we divide by 298. That gives us a value of 4.0 liters. So you can use these formulas to calculate either the final temperature or the final volume when you are given the other factors. Now, let's look at what we call the combined gas law. The combined gas law uses Boyle's law and Charles's law all combined together. So the air conditioners here, it makes use of all the three properties of gases: the pressure, the temperature, and the volume. So the pressure, the temperature, and the volume, they vary. So we are going to see the combined gas law equation. So the combined gas law equation states that P1 V1 over T1 is equal to P2 V2 over T2. Okay, so you can always use this formula to calculate any of the values, either the temperature, the pressure, or the volume, when you are given all the other quantities. We'll look at an example here. Now, a gas with a temperature of 280 Kelvin, a pressure of 200 kilopascal, and a volume of 25.8 liters is compressed to 15.8 liters, causing the pressure to increase to 350 kilopascals. What is the temperature of the gas under the new conditions? So we are looking for T2. What is the temperature of the gas under the new conditions? So one thing that you have to know here is that the units of pressure must always be the same. Here we have them to be the same. If you have the unit of pressure given to you in different units, you have to make sure you use the conversion factor and they must be the same. The volume as well. If you have liters and milliliters, you have to make sure they are the same. For pressure, let's say you had kilopascals and atmosphere, you must convert them to be in the same unit, either kilopascals or atmosphere. And for temperature, your temperature must always be in Kelvin. Now, let's collect data here. Our P1 is 200 kilopascals. Our V1 is 25.8 liters. Our T1 is 280 Kelvin. Our P2 is 350 kilopascals. Our V2 is 15.8 liters. And what are we looking for? We are looking for T2. So we are going to state the combined gas law, and then we make T2 the subject of the formula. So the combined gas law states that P1 V1 over T1 is equal to P2 V2 over T2. Now, we are now going to make T2 the subject of the formula. So T2 is equal to P2 V2 T1 over P1 V1. Now, we have all the information here, all the values. So we go ahead and substitute the values. So everything, as we are substituting, the units that appear at the bottom and at the top, we are going to cancel them out. So we have kilopascals appearing at the bottom and the top, we cancel out. The liters as well, we cancel out. And the units are the units of temperature in Kelvin. So that gives you a value of 300 Kelvin. Now, let me give you a little trick here. How do you know when to use the combined gas law, or when to use the Boyle's law, or when to use the Charles's law? For the combined gas law, if you have to use it, you will always be given 5 of the 6 values here. We have P1 V1 over T1 is equal to P2 V2 over T2. So you will always be given 5 of them. So in a situation where you see 5 of these properties given to you, you are going to use the combined gas law. Okay, 5. Now, for the Boyle's law and the Charles's law, when you are given 3 of the units, 3 of the factors, so you will always be given 3. Now, how do you know if you are using the Boyle's law or the Charles's law? Now, that is just going to depend on the units, the values that you've been given, the property. Is it the temperature and the pressure, or is it the volume and the pressure? So that is how you differentiate that. Now let's look at the other gas laws. So we've already seen the Boyle's law, the Charles' law, and the combined gas law. Now we are going to look at the Avogadro's law, and we are going to look at the ideal gas law. So the Avogadro law states that if temperature and pressure are constant, the volume of the gas is proportional to the number of moles of gas present. The number of moles of gas present. It doesn't matter the identity of the gas. So the volume is directly proportional to the number of moles, which means that at standard temperature, which means that V over N is equal to a constant. So volume is directly proportional to the number of moles. V over N is a constant. So at standard temperature and pressure, which is often abbreviated STP, the temperature is 0 degrees Celsius, which is 273 Kelvin. The pressure is 1 atmosphere, and we know that at standard temperature and pressure, 1 mole of a gas will occupy a volume of 22.4 liters. It doesn't matter which gas it is. The identity of the gas doesn't matter. So long as we have 1 mole, it will occupy a volume of 22.4 liters. So let's look at the ideal gas law. The ideal gas law states that PV is equal to nRT, where P is the pressure, V is the volume, N is the number of moles of the gas, R is the gas constant, and T is the temperature. So R is called the gas constant, and it has a value of 0.0821 liter atmosphere per mole Kelvin. So that is the unit of R. Now, the temperature must be in Kelvin, as I've told you. When working with gases, the temperature must always be in Kelvin. For the pressure and the volume, the units must be constant, so they must match each other. If you have different pressure units, let's say you have atmospheres in one value and millimeters of mercury in another value, you have to use the conversion factors that I've given you and convert them to have the same unit, either of them, either all millimeters of mercury or all atmosphere. Same thing for volume. If you have a volume that is given to you in liters and another one in milliliters, either you convert everything to liters or you convert everything to milliliters, and they have to be the same. Now let's look at an example here. What volume does 1 mole of gas occupy at a temperature of 0.00 degrees Celsius and a pressure of 1.00 atmosphere? Now, we have been given the number of moles. We've been given the pressure, and we've been given the temperature. So we are asked the volume. So in this case, we are going to use the ideal gas law. So let's state it. The ideal gas law states that PV is equal to nRT. So if we are looking for volume, we are going to make V the subject of the formula. So let's collect our data. The temperature is 0.00 degrees Celsius, and I say we must convert it to Kelvin. So that is going to give us 273.15 Kelvin. Now, the volume is going to be given by nRT over P, using this formula and making V the subject. So V is equal to nRT over P. Now, our values here, we know that the number of moles, N, is equal to 1.00 mole. R, which is the ideal gas constant, is equal to 0.0821 liter atmosphere Kelvin. Then the temperature is 273.15 and the pressure is 1 atmosphere. So we cancel out the units that appear on both sides and we are left with the unit of volume, which is liters. So if you solve out that question, you will see that your answer is 22.4 liters. Now, let's look at the situation where we have mixtures of gases. When we have mixtures of gases, the gases are going to exert pressures in the containers in which they find themselves. So the pressure that is exerted by each gas is called the partial pressure. And the total pressure is the sum of all the partial pressures of the gases. So, for example, here we have in this situation, we have nitrogen, which is 78%. Nitrogen, we have oxygen, and we have the other gases. So nitrogen will exert a partial pressure in this container. Oxygen will exert a partial pressure. So that is just the pressure exerted by oxygen. And then the carbon dioxide will exert its own pressure. So that is called a partial pressure. The partial pressure is the pressure caused by one gas in a mixture. And the total pressure is the sum of all the partial pressures. So let's look at an example that involves partial pressures here. If a 40.0 liter cylinder is filled with 5.00 moles of nitrogen, 2.00 moles of oxygen, and 3.00 moles of carbon dioxide at a temperature of 400 Kelvin, what is the pressure inside the cylinder? Here, we are looking for the total pressure inside the cylinder. So, for us to look for the total pressure inside the cylinder, we are going to calculate the partial pressures of all the gases, and then we sum them up. So, for us to calculate the partial pressure of the gas, we are going to use the ideal gas constant and relate it to each gas. Now, let's look at that of nitrogen. We know that PV is equal to nRT. So, P will be equal to nRT over V. So, if you have to look for the partial pressure of nitrogen, we are going to use the number of moles of nitrogen. We are going to use the ideal gas constant, the temperature of the medium, and the volume of the container that we are using. So, let's look for the partial pressure of nitrogen. For nitrogen, we have 5.00 moles. So, we are going to substitute everything in here. So, that is 5.00 moles times R times T over V. So, that is going to give us a value of 4.11 atmospheres. So, that is the partial pressure exerted by nitrogen. Likewise, we are going to calculate the partial pressure exerted by nitrogen, by oxygen, and carbon dioxide. So now let's calculate that exerted by oxygen. So we have 2.00 moles of oxygen. We are going to substitute 2 in this equation where we have N. So when we do that, we will have these values. And remember, we can always cancel out the units that appear both at the top and at the bottom, and we are left with units. So here at the top, let's do that for nitrogen. We see the mole here, cancel with the mole here. The liters here will cancel with the liters, and the Kelvin here will cancel with the Kelvin, and we are left with atmosphere. So that is the same thing that you will have for all of them. Now, if you do that for oxygen, you will see that the partial pressure of oxygen will be equal to 1.64 atmosphere. So everything still cancel out the same. The moles cancels, the liters will be the liters cancel with the liters at the bottom. The Kelvin here cancels with the Kelvin here. We're left with atmosphere. So that's the partial pressure of oxygen. Now we can also look at the partial pressure of nitrogen. Same thing for carbon dioxide. Sorry. So for carbon dioxide, we have 3 moles. So we substitute, and that is the same thing. Moles cancels with mole. Liters cancels with liters. Kelvin cancels with Kelvin, and we're left with atmosphere. So that gives us a value of 2.46 atmosphere. We've said that the total pressure inside the container is equal to the sum of the partial pressures. So the P total is P, the partial pressure of nitrogen plus the partial pressure of oxygen plus the partial pressure of carbon dioxide. So that gives us 4.11 atmosphere plus 1.64 plus 2.46, and that is 8.21 atmospheres. Now, in a second method, I'm going to show you how we could solve this easily. Now, let's look at the second method of solving this problem. So, in this problem, we have said the pressure is related to the total number of moles and not the identity of the gas. So, we could also solve this problem by simply summing up the total number of moles and using just simply PV is equal to nRT. That will still give us the same answer. So let's go ahead and sum the total number of moles. So we have 5 moles plus 2 moles plus 3 moles. That gives us 10 moles of gases totally. Now, we are going to use PV is equal to nRT, and we just find the pressure by simply dividing nRT over V. So our number of moles, total number of moles is 10. So the P total will be nRT over V. So we just substitute in N, which is 10, and then the other values. So if you do this, the units will still cancel out, and you are left with 8.21 atmospheres. Same thing like what we had in the previous slide, 8.21 atmospheres. So that's the same thing. So the second method is easier. It's easier because you understand that the pressure is proportional to the moles. It is related to the total number of moles and not the identity. Now, let's look at gases at the molecular level. So we are going to see what will happen if we increase the temperature or we decrease the temperature, if we increase the volume or decrease the volume, or if we increase the number of moles or decrease the number of moles, what is going to happen. So this is the situation here. We have this container here that contains these gases. Let's look at the scenarios. Let me label this 1, 2, and 3. So let's start with the first scenario. What will happen if we increase the volume? What will happen to the pressure? So we are looking at everything here in terms of pressure. What will happen to the pressure if we increase the volume? Now, increasing the volume, it means that the gases will have to travel far distances before they collide with the walls of the container. So, because they have to travel that far distances, the pressure reduces, because pressure is caused by the collisions of the gas particles with the walls of the container. Because the container is now large, the collisions are reduced, and thereby reducing the pressure. So if you increase the volume, pressure decreases. So let's look at the second case here. If you add more gas, so adding more gas to the container, the volume is still the same. So adding more gas means that there will be more collisions inside the container, because the gas particles are now many in the container. So they are going to hit the walls of the container frequently. So as they are hitting the walls of the container, they generate a force, and there the pressure also increases. So increasing the gas particles leads to an increase in pressure. Now, the third scenario, what happens when you increase the temperature? So when you increase the temperature, you increase the kinetic energy of the gas particles. And as the kinetic energy increases, the gas particles move faster. And as they move faster, the collisions with the walls of the container also increase, thereby increasing the pressure. So increasing temperature increases pressure, adding more gas increases the pressure, and increasing the volume will decrease the pressure. Now let's look at what is called diffusion. Diffusion is the spread of particles through a random motion, and lighter particles diffuse more quickly. Let's look at an example of diffusion here. Now, if by error the cooking gas in your room or in your house is open, so if you fail to close it, you sit at one end of the house, you will smell the gas. So the gas has diffused throughout the room. Take note here, I'm talking about diffusing throughout the room, because there is also a fusion. So another example is that if you sit in a room, if there are 2 or 3 people sitting in a room and they are sitting at different ends of the room, if one person farts, the other person sitting at the other end will be able to smell the gas. So it means that the gas has diffused throughout the room. Now let's look at effusion. Effusion is the process of a gas escaping from a container. So if you have a container that is filled with a gas, the process of the gas leaving that container is what is called effusion. Now let's look at the size and the relation to effusion. So lighter particles will effuse faster than heavier particles. if they have the same if they are put in the same container with the same opening, the lighter particles will effuse faster than the heavier particles. For example, helium here will effuse faster than air because helium is lighter than air. So if you have 3 balloons, one filled with helium, one filled with nitrogen, and one filled with argon, as time goes on, what will happen is that you will see that the balloon that is filled with helium would have, the effusion rate would have been very high because it is lightest. Helium is the lightest gas, so the effusion rate will be very fast. So you see it will reduce. Now, between helium, nitrogen, and argon is the heaviest of them all, which means that even with time, the effusion rate will be very slow. You see, nitrogen will effuse faster than argon, and helium will be the fastest because it's the smallest, the lightest. Now let's look at gas stoichiometry. In chapter 7, we looked at mass stoichiometry, where we were able to relate moles to grams, and then we relate grams to grams. So we are going to use gases, and we are going to use the stoichiometry and the gas laws to explain this. So, for example, in the process of fermentation, we are going to see how many grams of glucose can be used. If we use a particular amount of glucose, it's going to produce a particular amount of ethanol and carbon dioxide. So we have to calculate the amount of ethanol and carbon dioxide, the gas that is produced. So for us to be able to calculate the gas, we are going to use the gas laws and the stoichiometry. So here in this equation, we have glucose that is being in the fermentation process. It is giving us ethanol and carbon dioxide. So we have to make use of the balanced equations here. The balanced equation is very necessary. So how can we convert from the properties of the gas to the moles, the pressure, the volume, and the temperature? So the conversion here, we are going to use the ideal gas law, PV is equal to nRT. Remember, there was a map. There is a map that we use. I showed you the conversion map, how you can convert from grams to moles, how you can convert from moles to particles, and how you can convert from moles of A to moles of B. So here, to convert the pressure, the volume, and the temperature to moles, we are going to use the ideal gas law. Just like we saw in chapter 7, the mole map, we already saw how we could convert from grams to moles and from moles to particles. Now, we are going to also see how we can convert from moles of A to using the ideal gas constant to the pressure, volume, and the temperature relationship. Now, if we have to convert from grams of A to moles of A, as we already saw, we use the molar mass. If we have to convert from moles of A to particles of A, we use the Avogadro's number. If we have to convert from moles of A to the pressure, volume, temperature relationship, we are going to use the ideal gas constant. And if we have to convert from moles of A to moles of B, we use the mole ratio in the balanced chemical equation. So we can also convert from moles of B to grams of B using the molar mass. So that is the map, the mole map, and here we are including gases now. So let's see an example. In the fermentation process of glucose, how many moles of carbon dioxide are produced for each kilogram of glucose that reacts? If the reaction takes place in a sealed container and the gas occupies a volume of 8.10 liters at a temperature of 21 degrees Celsius, find the pressure of the carbon dioxide gas inside the container. So, this is the fermentation process. So we are asked to calculate how many, if we use 1 kilogram of glucose, how many moles of carbon dioxide are produced. So the first thing that we are going to do here, we are going to convert the grams of glucose to moles of glucose, from moles of glucose to moles of carbon dioxide, and then from the moles of carbon dioxide, we are going to find the pressure. So we are asked here, find the pressure of the carbon dioxide gas inside the container. Now let me give you the procedure again. We are going to use the kilograms here and convert it to grams. From the grams, we are going to use the molar mass of glucose to convert to moles of glucose. From the moles of glucose, we are going to use the balanced equation here to convert to moles of carbon dioxide. So after obtaining our moles of carbon dioxide, we are now then going to use the ideal gas law to find the pressure of the carbon dioxide. Now let's start. So we are moving from grams of glucose to moles of glucose, and from moles of glucose to moles of carbon dioxide. Remember here that you are given a kilogram of glucose. So we have to convert that kilogram first to grams. So a kilogram is equivalent to 1000 grams. So 1000 grams of glucose, we have to convert it to the moles of glucose. So we are going to multiply by the conversion factor. We know that 1 mole of glucose is equivalent to 180 grams of glucose. Now, we have our value here now in moles of glucose. So we are now going to use the balanced equation to move to moles of carbon dioxide. In the balanced equation, we see that 1 mole of glucose gives 2 moles of carbon dioxide. So the conversion factor will be 1 mole of glucose to 2 moles of carbon dioxide. And in this case, 2 moles of carbon dioxide will be at the top and 1 mole of glucose will be at the bottom, so that they can cancel out. So we cancel out here, and we have the moles of glucose. So we multiply by 2 over 1 mole, so that the moles of glucose here cancel out, and we are left with moles of carbon dioxide. So that gives us a value of 11.10 moles of carbon dioxide. That is the first part. How many moles of carbon dioxide are produced? So we've answered that part. Now, the last part, we are asked to find the pressure of carbon dioxide gas inside the container. So what we are going to use now to find the pressure, we are going to use the ideal gas law, which states that PV is equal to nRT, and the temperature must be in Kelvin. So we are now moving from moles to pressure. Now, P is equal to nRT over V, because we've calculated the number of moles, 11.10. R is equal to 0.0821 liters atmosphere per mole Kelvin, and the volume that we have been given here is 8.1 liters. The temperature is 21 degrees Celsius, so we convert 21 degrees Celsius to Kelvin. So we add 21 plus 273. Now we have 294 Kelvin, and we substitute the values in this equation. So if we substitute everything, we are going to have this equation, and we are looking for pressure. So let's see what cancels out. Moles will cancel with moles. The liters will cancel with liters. The Kelvin will cancel with the Kelvin. And we are left with atmosphere. So that gives us a value of 33.1 atmosphere of carbon dioxide. Now, let's look at another example here. Natural gas burns cleanly in air according to this equation. So we have methane plus oxygen to give us carbon dioxide and water. Remember, the equation must always be balanced. So we are using balanced equation. Now, if 13.1 liters of methane burn at a pressure of 1 atmosphere and a temperature of 290 Kelvin, what mass of carbon dioxide gas is produced? So we are given information here in terms of methane, and we are asked the mass of carbon dioxide. So what are we going to do in this case? So the first thing is that we are going to calculate the moles of methane. So because we're given in this equation, if 13.1 liters of methane burn at a pressure of this and at a temperature of this, so we are going to use the ideal gas constant to calculate the moles of methane. Then from the moles of methane, we are going to use the balanced equation to calculate the moles of the gas produced, which is carbon dioxide, and from there we are going to convert from the moles using the molar mass to grams. So let's go ahead. So we are going to move from the pressure the volume of methane and the temperature to get the number of moles. So the number of moles from PV is equal to nRT. We know that PV is equal to nRT. So we make N the subject of the formula. So N is equal to PV over RT. So we are going to substitute the values. We have the pressure of 1 atmosphere, the volume of 13.1 liters, the R that is 0.0821, and the temperature 290 Kelvin. So we see the units cancelling out and we are left with mole. So that gives us 0.550 moles of methane. Now with these moles of methane, we are now going to convert it to moles of carbon dioxide using the balanced equation. So in the balanced equation, we see that 1 mole of methane gives us 1 mole of carbon dioxide. So we will have the conversion rate that 1 mole of methane is equal to 1 mole of carbon dioxide, and we cancel out. Then we convert from the moles of carbon dioxide to grams of carbon dioxide using the molar mass. Now, converting from moles of methane to moles of carbon dioxide, then to grams of carbon dioxide. So we have 0.55 moles of methane. We are now going to use the conversion factor from the balanced equation. So 1 mole of carbon dioxide gives us 1 mole of methane. So 1 mole of methane gives 1 mole of carbon dioxide. So we see that the methane cancels out, and we are now left with moles of carbon dioxide. Now we have to convert the moles of carbon dioxide to grams of carbon dioxide. So we multiply by the conversion factor, which is the molar mass of carbon dioxide. So moles will be at the bottom and grams will be at the top, so that the moles of carbon dioxide cancel out with the moles and we are left with grams. So the conversion factor is that 1 mole of carbon dioxide is equivalent to 44.01 grams. Remember, to calculate the molar mass of carbon dioxide, you use the masses of carbon and oxygen in the periodic table. We already saw that in chapter 7. So this gives us a value of 24.2 grams of carbon dioxide. So the summary now, it shows us how to move from grams of A to moles of A. We have to use the molar mass. To move from moles of A to particles of A, we use the Avogadro's number. So moving from moles to particles, particles here could be atoms, the particles here could be ions, the particles could be molecules. So you use the Avogadro's number. Then to move from the moles to the ideal gas relation, we use the ideal gas constant. Now moving from moles of A to moles of B, we use the balanced equation and we make use of the mole ratios.